People have been converting biomass into energy and products in many different ways, one being the conversion of biomass into producer gas by gasification. During the Second World War, people made transportation fuels for their cars via the gasification of wood. South Africa later used this technology for converting coal during the oil boycott due to apartheid. Today, there are more than 272 gasification plants with more than 600 gasifiers operational worldwide, mainly focused on coal, oil and gas. For biomass, there are around 30 large-scale operational gasifiers. Gasification of biomass as a technology has received much attention despite still being in its infancy as a clean conversion technique providing chemicals and energy for humanity. Biomass gasification is the conversion of dry biomass primarily into CO and hydrogen, also called producer gas or syngas. This process can be performed via reaction with oxygen or an oxygen-delivering donor, such as steam, as shown in the reaction equations, which represent the chemical reactions during gasification of wood. Essential for gasification is the use of less oxygen than needed for complete combustion to CO2 and water. Why gasification? Gasification is a clean, reliable and flexible way to create producer gas from low-value feedstocks for the production of high-value products and power. Gasification is energetically more efficient than the direct combustion of biomass, has fewer emissions into the environment than direct combustion, produces producer gas that can be converted into chemicals and fuels via the so-called Fischer-Tropsch synthesis, and is proven technology. The challenges of biomass gasification are as follows. Biomass gasifies less easily than coal or oil. The required high temperature for gasification, bigger than 800 degrees centigrade, means the use of specific equipment and knowledge. Producing a clean and pure producer gas is difficult. The application of the producer gas is often limited by the presence of tar and/or dust. Most biomass gasification systems use air instead of oxygen for the gasification reactions, which is typically used in large-scale industrial and power gasification plants. Gasifiers that use oxygen require an air separation unit to provide the gaseous or liquid oxygen. However, this is usually not cost-effective at the smaller scales used in biomass gasification plants. This means that the biomass gasifiers are operated at a relatively low temperature, typically 850 degrees Celsius, resulting in incomplete gasification. Producer gas from gasifiers that operate at relatively low temperatures typically contain unreacted carbon in the form of tars. Tars comprise a wide spectrum of organic compounds, generally consisting of several aromatic rings. Tars tend to deposit, forming sticky deposits in locations that can significantly impair equipment performance and are difficult to remove. Which reactor systems are used for biomass gasification? Typical reactor systems used for biomass gasification are fixed bed, fluidized bed, entrained flow and multi-stage. Firstly, fixed bed gasification. Fixed bed gasification can be divided into downdraft, updraft and crossdraft. Biomass is fed in on top, while the producer gas may leave the gasifier at the top, side or bottom of the fixed bed gasifier. Fixed bed biomass gasifiers are only used for smaller sizes, below for instance 5 megawatt thermal. Fixed bed gasification of wood is used in Harbour in Denmark, Wiener Neustadt in Austria. Secondly, fluidized bed gasification. With this type of gasifier, air or steam is injected at the bottom of the gasification reactor. This upward air or steam movement results in the fluid-like behavior of the bed material and excellent heat transfer within the reactor. Fluidized bed gasifiers can be used for various capacities. Some European examples are Värnamo in Sweden, Arbre in North Yorkshire, UK, Skive in Denmark, and Amergas in Geertruidenberg in the Netherlands. Thirdly, entrained flow gasification. The biomass is often pulverized prior to gasification and, most often, a pressurized reactor is used with oxygen as a gasification agent. European large-scale and trained flow gasification examples have been developed in Baggenum, the Netherlands, and in Puertollano, Spain. These gasifiers were designed for coal and petroleum coke, but also admixed biomass to lower the CO2 emissions. However, the operation has been terminated from an economical point of view. Fourthly, multiple-stage gasification. The gasification process takes place with steam in a bubbling fluidized bed combined with a combustion section for the removal of the carbon deposited on the bed material and to supply the heat for the gasifier. This process produces a high heating value producer gas combined with a low tar content. A few European examples of indirect or steam gasification are DTU Viking gasifier in Lyngby in Denmark, Güssing in Austria and Milena in the Netherlands. The gasification processes of coal, oil and gas are well-established technologies working on a large scale, bigger than 80 megawatt thermal. Biomass gasification as a clean conversion technique providing chemicals and energy for humanity still needs development. It typically works on a smaller scale, smaller than 20 megawatt thermal and at lower temperatures. This lower temperature leads to the formation of tars in producer gas, making the reactor operation and cleaning of the gas more complicated. The removal of tars is essential for use of the producer gas in a gas turbine for power or Fischer-Tropsch synthesis for chemical production.